All right, so very quickly, I am going to go over charge and current density. I am a physics graduate student and spent a lot of time tutoring in undergrad, and this was one of the most confusing topics for students in physics to electromagnetism or introduction to electromagnetism. And so I wanted to record a YouTube video that will hopefully help future students who maybe are mixing up these concepts. So, what is current or charge density? For anyone that's had chemistry, it's the same as any other density, right? Density times volume is how we get the mass of an object. In chemistry, right, we're using the density of that object, how spread out the molecules may be within it. Um, but in terms of physics 2, we're going to need to find the density, our charge density, that can be linear surface volume, or our current density, include, when we're doing either Ampere's law, if you've gotten to magnetism yet, or Gauss's law for electric fields. Also, we need to find dq before we learn Gauss's law, or if we don't have symmetry that will allow us to use Gauss's law, we need to find dq. In order to find dq, we need to know what the charge density is per unit length. And just be clear, this only applies to uniform charge or current distributions. So again, I just mentioned when do we need to find it. These are some more visual examples. So top right corner, integration for electric fields or potential. So if they were going to give you this thin continuous line of charge, and they would say, okay, at point P, we're going to need you to find the electric field, you would need to find out how much of this slice, right? We know it has dq, but what is that value? Um, for Gauss's law, we need to find our Q enclosed. Ampere's law is similar with our current through or current enclosed. So for Gauss's law, right, we have this situation, this situation. The situation on the left, our Gaussian surface right here, that's not part of, that is not inside of our surface, right? So whatever Q that they have here, um, that would equal Q enclosed in this situation, right? Because we're outside. However, in here, there's some Q that's distributed throughout this surface uniformly, and we only want the Q that is inside our Gaussian surface right here. And it's the same for Ampere's law when we're talking about current, right? So we have current moving through some object. Again, if you are outside the object, right? If for this one, our current is just I. For this one, it's going to be our I enclosed or I through the loop. All right, so let's relate to what we know. We know what volume is, right? Here's all our objects. We know what area is. So let's talk about density in the way you're familiar with it, mass per unit volume. So anytime you have per, as you probably know from physics one, meters per second squared, um, per just means divide. So density is mass divided by volume. And again, in chemistry, these are your common units for density. So once you have the density of, say, water or aluminum, but let's go with water. It's a liquid. We have water. We know the density of water, and we know the volume of the container we want to place it in. Well, we can calculate what that mass is going to be by taking the density times the volume. So this is what we are familiar with. But now let's talk about physics, right? So instead of thinking about it in terms of current and charge density in the beginning, especially if this is something that confuses you, I always advise tutees or students, think of it as a sport, think about a sporting event, a concert, even a school play, right? There's capacities by the fire marshal, right? So how much space does a person require? And if we know how much space that person has, are we able to determine how many people can attend our event? I know that sounds confusing. Just bear with me. I'm going to get to the examples on the next slide. But right here, these are the three formulas that you're taught about: continuous charge distributions, uniform charge distributions, uh, right? Volume charge density. And if you notice, all of these are just Q divided by either your length, your area, or your volume. So that's the important thing to take away. Yes, you should probably know lambda sigma rho, but as long as you remember total charge divided by length, area, volume, you'll be able to calculate that. All right, so our first example, and we talked about this earlier, would be let's talk about linear charge density lambda. So again, that's going to be Q divided by L, and that's going to give us our lambda, our charge density. So when we have a problem, like in the bottom right-hand corner, we have point P. And in this case, right, this isn't necessarily Gauss's law because I don't really have symmetry. Although actually, I suppose you could use Gauss's law with a cylinder, but I'm going to do it. We have to integrate, right? So we have dx, and we know dx has some dq, right? And so we know for an electric field, so we know for an electric field, right, we have 1 over 4 k epsilon naught, sorry, 4 pi epsilon naught. And then that's going to be Q over R squared. And we have to sometimes find, and we know that this is just K. So K dq R squared. I'm not going to go over how to solve this problem. I will say, in terms of setting it up, my normal process is identify what's changing. Once you identify what's changing, you're able to set it up. So, for these types of problems, one, we know we're going to need to find dq. What is the charge, incremental charge in this slice? And then two, what's changing? And in this case, it's our distance, which is r. So, right, from this end to this end, there's going to be a different distance there. Fortunately, in this problem, right, our distance, r squared, is just going to be x squared plus y squared because they set that up nicely for us. I will say another problem they commonly give in physics is something like this with a ring of charge from 0 to L. You have a radius here. The radius is not changing, but your angle is changing. So whatever's changing, that's what needs to integrate. So in this example, example one, right, we need to integrate over the distance, right, from 0 to L. And that would be in terms of dx. In example two, right, we're going to be integrating from negative pi over 2 to pi over 2, and we're going to be integrating over some we need our integration in terms of theta, right? Because that is what's changing. All right, so now step one is what we're going to focus on. How do we find our dq? Well, normally they say, okay, this has Q, this is length L, right? So sigma is just Q over L. But that doesn't necessarily make this something that makes sense logically in your head. Electricity is new to a lot of students. And so we're going to think about our charges as people. So let's think again about a sporting event, a play, anything. But in this case, we just have benches. So we have benches um, that's 2 meter long. So we have one bench 2 meters long, as you can see in this picture, and we have four people, right? And so if you imagine those people, right, uh, uniformly spread out on a bench. So let's calculate our quote unquote people density. So we have four people over 2 meters, and that's going to give us two people per meter as our density. So now, in if I say, well, how many people will fit in 50 meters, right? We would take our people density times 50 meters, and we know it's 2 times 50 would mean we could fit 100 people. So again, if charge density is something that is confusing to you, think about it in terms of capacity. It's just like any other density. It's describing how dense a certain area, unit length, area, or volume is. In this case, charges could be current, but I'm using it with people. And I think the next example will help as well. Okay, so surface charge density, sigma, again, that's Q divided by our area. So let's just look at this VIP section right here. And we have seating. It's pretty uniform. And so we need to figure out what is our sigma? What is our density? How many people per unit? Well, first, we know our area, right, for a rectangle is length times width. So in this case, right, 5 times 10 is going to be 50 meters squared. And then we have 100 people. So we have 150 meters squared, and that's going to give us two people per meter squared. So then if I say, well, how many people can fit in 100 meters squared, right? You would be able to do that math and figure out how many we could fit, right? It would be 200 people. So again, all we're doing is this is the same process you're going to do, except with charges or current density, whether that's surface or linear. All right. A quick note I just wanted to make. I'm not going to go over volume density. You can think of, I'll show you an example you can think of after this to visualize volume. But for Ampere's law, this is magnetism. You may not be there yet. We have to find I enclosed, right? It's very similar to Gauss's law. And so in order to do that, first we need to think of the situation. Okay, so for R2, we're outside of the loop, right? All this current is in here. It's in this wire. So if our loop is outside that wire, then I enclosed is just going to equal the current. Where sometimes students run into confusion is when we're inside the wire. And the reason for that is because we're using the same formula twice. But it's different, and I've highlighted those differences down here, right? So first, we need to find the current density J, which is equal to I over A. And I personally, this is something that confused me, right? So we know I enclosed, let me back up 1 second, right? We know it's going to be current density of the wire times the area of our Amperian loop. I like to write wire loop because when you get down to these formulas, it's just easier to not get them confused. So first we need to find the current density of the wire. And we do that by taking the total current in the wire, dividing it by the area of the wire. Then once we have that second term, we can now calculate our I enclosed or I through the Amperian loop, right? And that's just going to be the current density of the wire, which we just calculated. But now it's going to be the area of our loop. So in this case, right up here, we would have I divided by pi r squared. I divided by pi capital R squared. And now the area of our loop is going to be pi r1 squared. Pi's cancel, and so you're left with r1 over capital R squared times I as our I through. All right. And then last example, you can just think of any stadium, right? Length times width times height, that gives you volume. So the total number of people uniformly distributed in this area. Or you could think about a swimming pool, whatever makes it easy for y'all. Thank you so much for spending time on this. Don't feel like you need to subscribe or comment. I'm not going to be posting regularly. I'm doing this for favorite students at my school, but any feedback is always appreciated. Thank you so much. Good luck on your exams.